everyone. You made it to our first lecture here for organic chemistry. This will do a brief introduction to chapter 1, which should be a review of general chemistry. There's a couple of topics specifically in section 8 that you might not have seen too far in depth in general chemistry, but we have talked about valence bond theory and VSEPR theory, hybridization, 3D shapes, electrons, bonds, things like that from general chemistry. And that's what this chapter is all about. It's a good way to get our foundation back from whenever you took general chemistry, whether it was last year or 5 years ago or 10 years ago, or you're just here because you love chemistry and you want to see what organic chemistry is all about. Welcome, wherever you may be from. So what we're going to see today is a starting off of wherever you have been, leave it at the door. Now, I like to start off with a little bit of a, stress relief meme slide, because a lot of people come to organic chemistry thinking, oh crap, what did I just get myself into? And I really want you to take a step and just take a breath and know that you are in good hands. This class is attainable. Anything that you may have heard before about it, let it go. Don't let your preconceived notions or things that you've heard from previous students tarnish your idea of organic chemistry. One thing that I want to make sure you do is you take each day as a new day and understand that I'm here to help you along this road. We are going to be doing a lot of things that look weird. As you start studying, people that aren't in this class, that haven't taken this class before, might just think you're doodling. I remember my parents thought that I could have just been making a whole bunch of stuff up when I would come home and do my homework. I lived at home during college. But what I really want you to start thinking about is this bottom right-hand corner meme. What you are going to be doing is learning a brand new language. Organic chemistry is nothing like the chemistry you've seen before because it's drawing based. We do touch calculators once or twice throughout the semester, but not often. And you are going to be speaking as if you are learning a new language. You're going to be able to start saying formulas differently, and what is a dash and a wedge and an OH and a CH3 and a CH2 and all these types of things. And that's what I want us to be able to come in with, knowing that things are going to look different. And that's okay. And be excited about that. One thing that you're definitely going to start doing is learning how to draw again. You might not have drawn for a while. We're going to draw. And it might look like we're just a shape drawing class. You're going to draw a lot of hexagons once we get into chapter 4. And that's okay too. I want us to be able to look at this new experience and say, it's still chemistry. It is still organic chemistry, but it might feel a little different to us. Now, we are going to start off with general chemistry. And things that maybe we have seen before, we look longingly towards and think back on the days of general chemistry when electron configurations were brand new to us and we thought that was complex. We're going to touch upon electron configurations again in this chapter, but we're going to move past them and just understand that they exist, and we're going to build upon their foundation, which is very important to understand them, but we're going to try to get through it quickly. Now, organic chemistry is the study of carbon-containing molecules and their reactions. We focus on one specific atom, carbon. Now, in a reaction, a couple of things that we want to be able to think about. Molecules collide with each other. They have to interact. They're not just holding hands and passing off one atom to the other. They are smashing into each other. Why do you think we use a stir bar in a lot of reactions to speed it up? You have to get those molecules to collide. Now, what that means is some sort of bonds broken have to occur. The reactants have to react. Something has to break. Along with that, bonds could be formed. To make new products, we have to be able to think that a new bond could eventually form. What we're going to be able to see in this class is the idea that two things can come together to create a new bond at the same time as kicking out or breaking another bond. Now, this reaction here is one that we're going to learn in chapter 7. We see the oxygen has a negative charge. That oxygen is going to go and what we call attack the carbon. It's going to create a new bond with the carbon, namely this one right here. In turn, that carbon kicks out the iodine. Iodine gains that negative charge by gaining a new lone pair. And therefore, what we see is a reaction where a carbon-iodine bond broke and a carbon-oxygen bond was formed, all at the same time. Now, what's really important for us is that when we start diving into organic chemistry, we're going to start with our foundation again in chapter 1. We're going to look at the atoms, we're going to look at the molecules, we're going to be able to build up into our Lewis structures and some other types of structures throughout this whole process. However, once we get into reactivity, this is the real meat of organic chemistry, are the reactions. So once we get into reactions, we're going to start with acid-base in chapter 3. But what we really need to focus on are the electrons. If you do not focus on the electrons, if you just start to memorize, organic chemistry is going to be very difficult for you. So as we start to practice and review our general chemistry items, know deep down where we are headed, reactions. And once we start seeing the reactions, really try to form a way of looking at the reactions that works for you, because if you don't find comfort in looking at a reaction somehow and you resort to memorization, you will fall behind and it will not be a very pleasant journey. But as we dive into the reactions, we want to make sure that we are communicating with each other. So always try to find some tips and tricks when looking at these, but know your foundation is always and always will be general chemistry. Now, why do we distinguish between organic and inorganic compounds? Well, organic compounds contain carbon, right? Inorganic compounds are the other heteroatoms, nitrogens, oxygens, hydrogens, things like that. Organic compounds are very important because they make up a lot of things. You and me and everybody in this class, we are walking, talking organic reactions. How can we ever think about how we process food, how we can heal in pharmaceuticals, how we can make clothes or plastics? We can't talk about any of those reactions without first knowing about carbon and its reactivity as an organic molecule. So when we think about where we have come from and where we are now, organic reactions weren't well known at the turn of the 20th century. 1900, we didn't really know what the difference between organic and inorganic was. Organic was things that came from living beings. That was the original definition. Now we just know it's essentially carbon. Inorganic is everything else, or what scientists back in the day said, non-living things. And so when we think about organic chemistry, we are going to be seeing a lot of carbon and focusing on it. That doesn't mean we won't see nitrogen and we won't see oxygen. There are going to be heteroatoms within this subject, but it's always going to be carbon-based. Now, organic does not mean non-pesticides. That's just a very, very bad terminology that we used a long time ago. If you think about a pesticide, it is carbon-based, right? So when we're talking organic, we're talking about every single carbon atom ever. And so what I want us to be able to do here is start to bring about real life examples within lecture, within class, within our time together. And so organic for our definition is anything that is carbon based for its molecule. Now, in the mid 1800s, it was first suggested that substances are defined by a specific arrangement of atoms. Why is a compound's formula not adequate to define it? Well, because the actual arrangement or the structure, this kind of is hinting towards the idea of, you've heard this phrase, structure dictates function. The structure of something is extremely important to define, not just the molecular formula. And that's because compounds with different structures could have the same molecular formula. Things like C2H6O. There's a molecular formula. That's not a structure. That's a molecular formula, and that tells me that there's 2 carbons, 6 hydrogens, and 1 oxygen. Well, I could think about arranging those in a row in my Lewis structure, where I have the 2 carbons and then the oxygen. If I were to review Lewis structures, I'd see how this could satisfy that definition. But what about this structure, where I had the carbon sandwiching the oxygen? These are what we call constitutional isomers. Now, an isomer is going to be anything that has the same molecular formula, but different structure, different orientation. Specifically, a constitutional isomer is going to be a molecule or a pair of molecules with the same molecular formula, same atom count, but different structures or different connectivity. These two are extremely different compounds. This is ethanol. We drink that if we're older than 21. This is dimethyl ether. Definitely not drinkable at all. Their properties, their physical and chemical properties, are completely different. Dimethyl ether has a boiling point at negative 23 degrees Celsius. It is a vapor at room temperature. Ethanol has a boiling point of 78 degrees Celsius. It's a liquid at room temperature. Yet they have the exact same atom count, but their connections, their structure is different. And so therefore we cannot define a molecule by its molecular formula, but only by its structure. And so we are really going to be diving into understanding the structure, the Lewis structure, and not just one central atom molecules anymore. We're going to branch out and see bigger molecules, because those are the ones that we deal with on an everyday basis. All right, so just to remember some of our rules from looking at Lewis structures, atoms that are most commonly bonded to carbon are nitrogens, oxygens, hydrogens, and the halogens, fluorine, chlorine, bromine, and iodine. Those are the ones that we are going to see most often. So not the entire periodic table, but a very small subset. Essentially, it's going to be rows 1 and 2, and then column number 7A or 17, the halogens. Now, with some exceptions, this is a good place to start. If we remember our Lewis structures and our Lewis dot atoms, carbon has 4 valence electrons. We used to draw it with 4 dots. What that means is that to reach an octet, carbon needs 4 more electrons. 8 minus the 4 valence is 4. So carbon generally forms 4 bonds. That doesn't mean it can't form 3. It can, but this is typical bonding. Nitrogen had a Lewis dot atom with 5 valence electrons. Nitrogen had 5 valence. It needs 3 more to reach its octet. So therefore, nitrogen generally forms 3 bonds. Oxygen, Lewis dot atom with 6 valence electrons. He needs 2 more, so oxygen generally forms 2 bonds. Hydrogen, or the halogens, I'll just choose fluorine. Halogens are also represented as X, as you see on that chart. They both need 1 more electron. Hydrogen reaches a duet because it's in row 1. It only has room for 1 more electron. Fluorine only needs 1 more to reach his octet, so those only generally form 1 bond. Now, these are general rules. We'll see some exceptions. We've seen exceptions before. Some exceptions to think about. Boron was a big exception to only bring 3 electrons to the table, so he generally makes 3 bonds. Or third row atoms and below, when they could expand their octet. So the incomplete octet in boron and the expansion of the octet in things like sulfur and phosphorus, those were common things we saw in general chemistry. Those still hold true today. We don't often see them, but we will be able to see boron and sulfur and things like that doing what they do best, be exceptions. Now, in covalent bonding, what we want to be able to think about and remember is a covalent bond is a pair of electrons that is shared between 2 atoms, specifically between 2 nonmetals. If we remember why nonmetals share electrons rather than transfer, like in ionic bonding, is because those nonmetals have a very, very high ionization energy. They don't want to give up their electrons. And they have a very, very high electron affinity. They love electrons, so they tend to share. Now we can think about these hydrogens coming together to form that covalent bond that we see. Now the sphere is trying to mirror that 1s orbital that the electron configuration of hydrogen portrays. And when we bring them together, what's really important that we remember is the idea that there is a specific bond length and a specific bond strength. Now, that bond length is defined as the internuclear distance between the 2 hydrogen atom nuclei. That's important to remember. Every single bond has a different bond length depending on what 2 atoms are sharing the electrons. And every unique bond also has a specific energy. When these 2 atoms come together, we can see our starting point right here. As we start to bring these 2 atoms together closer and closer and closer, there is a sweet spot that is that lowest energy possible. When we make bonds, we release energy. The reason why that happens is because of the attractive forces between the nuclei of each atom and the electrons being shared. But specifically, it's the protons to the electrons. That attraction is holding the 2 atoms together. Attraction is favorable, energy releasing. Exothermic, if we remember that terminology from general chemistry. Now, other things are also happening. Why don't we just collide the 2 atoms and get them closer and closer and closer together? Well, because with attraction, there's also repulsion. Now, what is repelling? The protons in the nuclei. The 2 nuclei cannot be on top of each other. The protons will start to repel each other, like charges repel. The other repulsion that we have are the electrons that also reside around the rest of the atom. So when we're looking at these two different types of forces, attraction releases energy, repulsion absorbs energy, endothermic. So when we think about these two, there is a balance to make that covalent bond. And when a covalent bond is formed, overall, the bond energy will always be negative, in terms of the idea that when we make the bond, we release energy. Energy will always be released when we form a bond. We'll talk about bond dissociation energy in just a little bit. When we think about dissociating a covalent bond, pulling it apart, that's when we think about the opposite sign. Hydrogen diatomic, making H2, releases 436 kilojoules per mole. When we break apart H2 into the atoms of two hydrogens, that's when it takes energy. So one thing I want to leave us with here before we get there, bond formation, energy released, exothermic. Bond breaking, energy required, endothermic. One simple way that we could think about that in real life is looking at magnets. Magnets are opposites attracting, right? Your refrigerator is one pole, and the magnet that has, the Care Bears on it, if you're at my house, is the opposite pole. So when I put that Care Bear magnet on the refrigerator, it sticks. It forms a bond, and it stays there, right? Now, if I wanted to break that bond, all I have to do is pull off the magnet. But me, physically, the surroundings, pulling that magnet off the refrigerator is the energy required to break the bond between the Care Bear magnet and my refrigerator. All right. So just a little review of general chemistry again. Protons have a positive 1 charge, neutrons are neutral. That's what's in the nucleus. So when we say nuclei are repelling each other, we're focused specifically on the protons, the like charges that are repelling. Electrons reside outside in the electron cloud. Those are a negative 1 charge. The valence electrons are the electrons that go into reactivity. They are the ones that we want to focus on. So when looking at, and let's just take carbon because he's our favorite child. Carbon has an electron configuration of 1s2, 2s2, 2p2. Now, which electrons are the actual valence? It's anything in the outermost shell, the principal quantum number, that is the final one our element has. Now, the 1s2, that is what we called core. They are stable. They should be a noble gas configuration, and they do not react, ever. We don't like them to react. They're super stable. They're couch potatoes. Do not make them get off the couch. Anything in that outermost N equals 2 for carbon, these are the valence. So S and P count towards those valence. So there are 4 valence electrons for carbon. Those are the ones that get to go into bonding, right? That's how we made our Lewis dot structures. Now, counting valence, you can always calculate the number of valence by looking at the electron configuration. But a quick and easy way is to just practice looking at the periodic table. I have the main group elements here, right? Who cares about the transition elements? No, they're very important. They are. If you wish to study them, that is inorganic chemistry. Excellent, excellent subject. But I chose organic. I like to just focus on carbon. So I'm a little biased. But if we look at just the main groups in this class, rows 1A through 8A. Now, 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, 8. Remember, the octet rule was there for a reason. The noble gases are extremely stable. And so when we're looking at the periodic table, a quick and easy way to identify the number of valence is just to look at the group number. You will always have a periodic table with you on an exam. You should always have a periodic table with you when you're watching these. Take a pause on the video. Go grab one. It's in your book. Or you can Google it. Okay, welcome back. Now, simple Lewis structures. Now, when we're looking at Lewis structures, we did a couple of different ways of identifying this. And depending on where you learned general chemistry, you might have taken the simplistic route, where you just draw the individual atoms using the dot representation. So if I were to think about the dot representations I just did for a couple of those, and we'll do NH3 here. So I'm going to draw 1 N and 3 hydrogens. Yes, you might be able to say, well, hey, could those guys go together? And those guys go together? And these guys go together? And your answer is yes, absolutely. You can start thinking about the Lewis dot structure as just a buildup of sharing those electron dots between two different nonmetals. And whenever we saw a bond, we changed it to a solid line. Yeah. This was a bond, or what we called bonding electrons. The lone pair that was left over, non-bonding or lone pair, right? Those are all good things to remember. Now, that's a nice way of being able to simply put the atoms together, right? We just drag them and say, okay, we'll pair them up. Now, it doesn't work that well when you have more than just a couple of atoms, or if you have double or triple bonds. So this is a good way to start off, but if you need a little bit extra practice, go back into how we did it in general chemistry. Find the central atom. This will help us for a few of our beginning examples in class. Once we get into more complex structures, we'll see that there might be more than one central atom. And then count the valence. So for this example, CH2O, carbon makes the most number of bonds. That's why he's going to be in the center. And then I'll put my other atoms around him. Counting the valence, carbon brings 4 electrons, oxygen brings 6 electrons, and each of the hydrogens brings 1. So we have a total of 12 electrons. 2, 4, 6 go into making the actual bonding pairs, right? You got to bond the 2 atoms in the first place. And then the other 6, we can start by putting in the octets for the outer atoms first. Hydrogens only have a duet, so that's why I didn't put lone pairs around hydrogen. Oxygen, we can put the other 6 as lone pairs, remember 2 at a time for Lewis. But when we look at this structure, we can say, hey, I don't have an octet for carbon, so what do I need to do? I need to share one more bond and make a double bond. So step number 3, complete octets. We start with the outer atoms first, and then if we need to make octets with the central atom and we don't have any more electrons left, we make double or triple bonds. We will practice this a lot more in class. We will get very, very good at these Lewis structures again, but again, rapidly. Okay, couple of things with formal charges. An anion is a negative charge. A cation is a positive charge. You may have seen these more often with the polyatomic anions. We're going to see them all over. We're going to see molecules that are big and bulky, but also have charges. And so we can call these anions and cations just how we had before. And atoms and molecules are typically neutral, but they can also have charges. To determine the formal charge for an atom in a given molecule, we have to compare the number of valence to the number it owns. If you had me for general chemistry, then you know I've used that terminology before. But essentially, when we look at the formal charge calculation, we can say it's the valence minus the number of lone pairs minus the number of bonds. That's what we mean by owned electrons. So in a specific structure, we can say something about the lone pairs that an atom owns and the bonds that an atom is participating in. Those should balance based off of how many valence that the atom brought itself. So if we look at this structure, let's go ahead and take that simple Lewis structure and convert it into a line Lewis structure, putting dots where there's lone pairs and straight lines where there's bonding electrons. Now, carbon typically bonds with 4 bonds, right? To reach his octet, he usually has 4 bonds. This is where we would look at carbon and say, yeah, his formal charge should be 0. He's bonding typically. That's awesome. However, we can do the formal charge calculation. This is for carbon. Carbon brought 4 electrons to the table. He doesn't own any lone pairs, and he has 4 bonds. Overall, his formal charge is 0. He's neutral. Excellent. Now for oxygen, he doesn't look like he's bonding typically. Oxygen typically, we said before, is divalent. It makes 2 bonds. We've only given him 1. So what we have to look at here is the formal charge for oxygen. He brought 6 electrons to the table. He owns 6 electrons that are lone pairs. 1, 2, 3, 4, 5, 6. And he owns 1 bond. There's a -1 overall charge. That means we have to put a formal charge on top of that oxygen. We can do that a couple of different ways. We can write that -1. We can just write a negative. We can negative and circle it. That's typical too. I try to not circle just to keep my my images here clean and neat, but feel free to do any of those. You can even do 1 minus. I like just minus. The only time you actually have to have the number there, the formal charge is greater than 1. Greater than +1 or greater than -1. Then you actually have to put the number there. I'll just put a negative. Okay, with polar covalent bonds, we talked about electronegativity. Now, an electronegativity is very similar to the electron affinity that is sometimes talked about in general chemistry textbooks. For us, when we talk about electronegativity, we're referring to these electronegativity values on a chart. You don't need to memorize these numbers, but you will not always get this chart. So a couple of things that you want to make sure you understand is that when we're looking at this chart, we're going to be able to look at a bond between 2 atoms and say, what is the difference in the electronegativity? We should always remember that fluorine is the most electronegative atom. Electronegativity increases going from left to right on the periodic table, and that's because the Z effective, the nuclear charge, is increasing, right? The number of protons in the nucleus is increasing, so it's pulling on those valence electrons tighter, so it wants more of those valence electrons. It also, electronegativity increases going from bottom to top. Our small atoms are more likely to want electrons more. As N decreases, the size of the atom decreases. The valence electrons are being held closer to that nucleus. So when we put another electron in there, that nucleus can feel the attraction more. I like to think about this example a couple of different ways. The one that you'll hear me repeat a lot is the idea of Red Rover. Everything you need to know you learned in kindergarten, right? So if you were lucky enough to be able to play Red Rover in kindergarten, you remember you stand next to your friends and you hold hands and you say, Red Rover, send so-and-so right over. And somebody on the other side of the field comes running and tries to break through the bonds that you are holding on to your friend. The tighter you hold on is more likely because you and your buddy are standing closer together. So we always want to think about how big an atom is or how small an atom is, and think about the pull, the strength. Just like if you were standing really, really close to somebody, you can hold on to them really tightly. If you're standing very, very far away, spread out your arms as you're listening to this lecture. If you spread out your arms and you try to hold on to something very, very far away, your grip is not as strong. So the pull on that very far away thing is not as strong. Same thing with electrons. We'll act that out in class later. Now, there are three general types of bonds. Covalent and ionic are the main two, but there's also this middle gray area of polar covalent. Now, when the electronegativity difference is less than 5, change in electronegativity is 0 to 0.4. That is what we call a covalent bond, equally sharing of electrons. These two you should know. Carbon to carbon, or any identical atom to atom bond, or bromine to bromine, oxygen to oxygen, that would all be a change in electronegativity of 0, covalent. Carbon to hydrogen, you're going to see a lot of carbon to hydrogen bonds. Those are covalent, what we call non-polar covalent. Their change in electronegativity between carbon and hydrogen is not big enough to have the electrons shifted towards one atom or the other. A polar covalent bond is when we have that electronegativity difference of 0.5 to 1.7. If we have an electronegativity difference of that, what we actually get is an unequal sharing of electrons. We've maybe have seen the dipole arrow before. Oxygen is more electronegative than carbon. Oxygen's electronegativity is a 3.5. Carbon's electronegativity is a 2.5. Specifically for this example, that change in electronegativity is 1. Oxygen has a higher electronegativity, so he is more negative. He's not an actual minus charge, but he is a delta. This is a delta, or a partial negative. Carbon is less electronegative, so he is actually feeling slightly electron deficient. He's a delta positive, or a partial positive. When we look at these deltas, the lowercase d with the plus sign is your partial positive, or delta positive. The little lowercase d delta with the minus sign is your delta negative, or your partial negative. Not actual charges, not ions, just an unequal sharing of the electrons within that bond. We'll talk about what this means for reactivity in chapter 3. Now, an ionic bond, the electrons are not shared at all. They are actually transferred. So there is this threshold now of the change in electronegativity. Now, electronegativity is greater, electronegativity is a difference greater than 1.7 is going to be our ionic bond, where instead of partial positives or partial negatives, instead of the line, what we actually see here are charged particles where the electron was transferred itself. So, spectrum, right? Electrons tend to shift away from lower electronegativity atoms towards higher electronegativity atoms. The more electronegative something is, the more it pulls on the electrons, to the point to which we may become ionic. Now, some bonds are acceptable to write as covalent, specifically carbons, but with our carbons, what's really important to remember, we'll see this where a carbon bonded to a metal is sometimes really close to just be writing the cation and the anion, right? What we see on the right-hand side here. But what's important to note is the reason why we could also draw it on the left-hand side is its electronegativity difference is on the cusp of the between polar, covalent, and ionic. And so either is acceptable. We'll be able to see both of these, but what's really important to note is still the idea that carbon is more electronegative than lithium, right? And really a good representation is just being able to ionize those between a metal and a nonmetal. We'll practice a lot with this. So the absolute difference in electronegativity is to be taken with a grain of salt, but it's a good kind of road for us, right? We don't want to say just because it's electronegativity differences here, for this example 1.5, that it has to be a polar covalent bond. We know in reactivity it reacts more like ionic, but it's a good guidelines, right? Now, with atomic orbitals, what we want to be able to remember from general chemistry is that quantum mechanics was established as a theory to explain the wave properties of electrons. If you remember Schrodinger's cat, which we'll tell the story in class, Schrodinger's cat was a thought experiment to identify the idea of wave-particle duality. And so the wave function is a plot of the probability of where we could find an electron in the electron cloud. We can remember on an XYZ plane, we think here, Y, X, and Z, however you like to remember your XYZ 3D Cartesian planes. The S orbital was a sphere, and the P orbital was a dumbbell shape, or the figure 8. And these were all probabilities, with one side shaded one color, the other side shaded with another color. All of these were probabilities of where we could find the electron in a given electron cloud. And so it's really with these shapes that we're understanding the idea of electron density, right? Again, it's a probability. It's not an exact location, but what we want to be able to think about is these are where the electron density could reside, the actual volume, the space occupied by an electron itself. Now we see that there are sometimes shades specifically for those p orbitals. The electron can behave both as particles and waves. So this idea that it can have wave-like nature where there's these hills and valleys, right? And so there's positive and negative really nodes separating these positive and negative areas of the probability. And so you'll see specifically the p orbital is shaded red and blue in textbooks. You might see for our purposes and for our drawings that we just shade one side and we leave the other side white. You could do it the other way where you shade the bottom We just don't ever want to see, this is a big old N-O, no, don't do this, the whole thing shaded, right? It's not all one color. Don't do that. It's not all blank either, right? Yes, this is the shape of a p orbital, but you got to shade it somehow. So be very, very careful with that. We are trying to understand the full in-depth craziness of quantum mechanics in a simplified way. It doesn't mean that there's a positive charge or a negative charge depending on where the shading is. It's just looking at the sign of the wave function. And so we'll take that simplistically. Now, electrons are most stable in lowest energy orbitals. So we start with the 1s, and then we went to the 2s, and with the n equals 2, we got the 2p x, the 2py, and the 2pz. We got degenerate orbitals. We can think about our electron configurations. We'll see the orbital diagrams in just a minute. I just want us to focus on the difference between 1s and 2s. Notice the 1s is smaller. As n increases, the size of the orbital increases. We will focus mainly on s's and p's. Since we are dealing mainly with the first and second row of the periodic table, we don't do a lot of d's. Even going into things like expanded octets, we usually don't even talk about hybridization past sp3. We don't talk about the 5 or 6 domain molecules. We usually stick with tetrahedral or trigonal planar. Things hopefully are starting to have us remember these terminologies. But looking at our 1s orbital compared to our 2s here, size is the big difference. And then with the 2p's, it depends on whether it's on the x, the y, or the z axis, right? That's how we define those degenerate orbitals. And if we remember the word degenerate, they were all equal in energy. Doesn't make a difference. The y, the x, or the z are all the same energies. And so when we started to draw the electron configurations from the orbital diagrams, we used just the build-up model, right? The Aufbau principle. And when we got to the 2p's, we used Hund's rule. You put one in each before you pair. Pauli exclusion principle, we can only have 2 electrons in a specific orientation at one time, as long as they were opposite spins. All of those about our electron configurations still hold true. They are very, very important for us. So hopefully you still remember them from general chemistry, and we can move on. Now with valence bond theory, it's talking about how do those atomic orbitals, s's, p's, t's, how do they overlap? What do they do when they do a Venn diagram to bring the shared internuclear distance together? What is happening? Now, if we remember a little bit about constructive and destructive interference, if we are bringing waves closer together that are constructive, they form one big space. This is good. This was bonding. If for some reason we bring opposite phases together, this is what we call canceling out or destructive, when a node appears in the middle and we start to see insufficient bonding. The bonds for an H2 molecule, hydrogen diatomic, result from a constructive interference. So if we can think about the 1s orbital with one electron and the other 1s orbital coming together with the other electron, what we tend to start to see is just a big ol' cloud or a Venn diagram of bringing them together. Direct overlap was the key word. And that is what we called a sigma bond. We abbreviated it with sigma as well. Now, when the orbitals directly overlap each other, head-on overlap, that is the strongest type of bond. We'll talk about parallel overlap in just a little bit, the pi bond, once we get there. Now, in molecular orbital theory, This is where we started talking about bonding and anti-bonding orbitals. We might not have gotten too far in depth with them for general chemistry, so let's just see what happens. If we take two atomic orbitals, these guys, I'm going to abbreviate those AOs, atomic orbitals. If you put two things together, you're going to get two things out. Bonding is always favorable, lower in energy. This is what we call a sigma bond or a bonding MO. But when I put two things together, I always get something that is destructive as well. I get the constructive, which is bonding, and I get the destructive, which we'll call the sigma star, little asterisk up there. Sigma star is how we phrase it, or we call it the anti-bonding. We won't spend too much time discussing anti-bonding MOs, but we will see them a little bit in chapter 4. Singular MO right there. Now, when we think about looking at that MO diagram right in the middle, right, I'll highlight them blue right here. These are molecular orbitals, the sigma and the sigma star, the bonding and the anti-bonding. When I look at those and I take the two electrons that I had, one from either side, one from either hydrogen, I would put them in the lowest energy orbital. That's the Aufbau principle, right? That is why H2 exists. There are two electrons in bonding and there are no electrons in the anti-bonding orbital. Now, when we look at this idea in terms of Venn diagrams, in terms of the constructive versus destructive, looking at the node in that anti-bonding orbital, this is unstable. That was the destructive interference. Over here, bonding, stable. It's the constructive interference. Now, there's a couple of other things that we're going to talk about later on that I just want to make sure that we present. The lowest unoccupied molecular orbital, or the LUMO, is this one right up here. This is unoccupied. There's no electrons in it, and it's the lowest unoccupied molecular orbital. The highest occupied molecular orbital is the one right below it, right? This threshold right here in between these two MOs are where we can start talking about excited electrons and relaxed electrons. The HOMO and the LUMO will be important for us when we start to think about ground state electrons. Now, we want the HOMO to be filled, the highest occupied molecular orbitals, and the LUMO, lowest unoccupied molecular orbitals, to be unfilled. We'll do a lot more work with the HOMO and the LUMO next semester. I wanted to present it here so that you knew it has its place in molecular orbital theory. Now, with hybridized molecular orbitals or hybridized atomic orbitals, what we really want to be able to say is that when we think about carbon and its orbital diagram, let's just look at it here. Energy increasing along the Y. We have the 1s, 2s, and the 2p. We'll do for carbon, since he's our favorite child. Carbon has 6 electrons total, and what we see is this would be his atomic orbital diagram, or we can even think about his electron configuration. This doesn't make sense why carbon would bond with 4 equal bond length types of carbon to hydrogen bonds. In methane over here, CH4. Why does it form the 109.5? Why does it form the tetrahedral? Well, what happens with carbon is actually very interesting. We have come to the idea that the atomic orbitals can actually homogenize or hybridize. This was our idea that where we have our valence electrons, just the valence, right? We'll leave the core, and we'll take those valence and we'll hybridize them. Now, hybridization involves the linear combination of atomic orbitals. The linear combination of atomic orbitals is a really, really complex mathematical operation that helps us understand how these s and p orbitals can homogenize themselves together to form degenerate orbitals. Now, think about cupcakes. Everybody's made cupcakes or seen people make cupcakes. Watch an episode of Cupcake Wars if you need to. Think about it. You take flour, sugar, eggs, milk, maybe some flavors. You're making funfetti, you throw in some sprinkles, and you mix it all up together. All of those different ingredients get homogenized and baked into equal looking, hopefully, cupcakes that are delicious, all tasting the same. That's hybridization. We want to take S and those 3 P's, mush them together, bake them into a cupcake. And so we take the S and the 3 P's, the X, the Y, and the Z, and we make them into equal energy orbitals that we'll call sp3 because we took an s orbital and 3 P's. Now, what happens to those electrons in the valence for carbon is now they're degenerate. Now they're equal in energy. Now they can all bond the same way. For the carbon atom, only 2 electrons are unpaired, and therefore it really can only share 2 electrons in its ground state electron configuration. Hybridization is the key to understand that there can be 4 equal unpaired electrons to form 4 equal bonds. Without hybridization, we cannot explain why CH4 is a tetrahedral molecule. So it's very important to understand how carbon makes those bonds. Now, carbon must undergo that hybridization to make 4 bonds, to be symmetrical in its geometry, that tetrahedral. And so this is a diagram where we can start to think about those 4 electrons are reorganizing themselves into 4 distinct degenerate orbitals. What results is the sp3 orbital is kind of like an S and a bunch of P's fell in love, had a baby, and it looks kind of like a dumbbell, but it's an uneven dumbbell shape, right? We see a bloated lobe there on the red side and a smaller lobe on the blue. You can also draw it without carbon involved, right? Don't forget your shaded side, at least one shaded side there. And so looking at this, it's 25% S character. We took 1 S and we took 3 of the P's. Those are the 75% P character. We mushed them all together. And so when carbon bonds with hydrogens to make CH4, we take that 1 S orbital and we take the sp3 orbitals and we merge them together. So we have a carbon that is sp3 hybridized, bonded to a hydrogen that is S atomic orbital unhybridized. Normally, it's the central atoms that get hybridized. Outer atoms can hybridize too, but hydrogen can't. Hydrogen just has an S electron. It doesn't need to do that. And so we see that all of those 4 bonds in CH4 are equal. And so they have to spread themselves out. This is valence shell electron pair repulsion theory, VSEPR theory. When we think about spreading out those groups evenly so that they don't repel each other, that they're given enough room. And that's where we get that tetrahedral is the 109.5. This is one of the most important shapes that we have in organic chemistry, carbon with 4 groups, tetrahedral. Anything that has those 4 groups will be sp3 hybridized. Remember the 4 electron groups For a central atom, it will always be sp3 hybridized, tetrahedral as its electron geometry. We'll talk about molecular geometry in a little bit. And then 109.5 degrees for the bond angle. Now, it doesn't mean that carbon can't bond other ways. Consider ethene or ethylene. C2H4. Lewis structure looks like this. Three-dimensional structure is that blue shaded planar structure. So when we look at carbon here, again, what we want to be able to think about, I'll just draw carbon's valence electron orbital diagram here. Same one that we had before. This is for carbon, just for its valence now. When we think about carbon here, let's look at one at a time. We have 3 electron groups. So we only need 3 atomic orbitals to make 3 degenerate hybrid orbitals. The 2p stays up there. These become the sp2. We took an s and we took 2 of the p's. We're counting up electron groups. We still can put 1 of each electron in there. The p is very close in energy to the sp2. They're not that much difference. But what we see now is a different hybridization, a different type of bond. With that carbon atom, think about carbon right here in the middle. Let me make him a little bit darker. Carbon atom right here. He's got his 3 sp2 orbitals, the 3 hybrid orbitals. He's got this leftover p with the lobe on the top and the lobe on the bottom. That leftover p, if we remember, this is where we can have a pi bond. Sigma bonds are where we get our hybrid orbitals. And sp2 is very similar to the sp3 in terms of shape. Big old difference here is it's going to have a little bit more s character, so think about it being a little bit smaller, a little bit looking more like a sphere. When we look at that ethene molecule, again, we see that there's an orbital overlap right here between the 2 carbons. Carbon that is sp2 hybridized bonded to another carbon that is sp2 hybridized. And here is that extra p orbital. That would be the pi bond. A carbon p to another carbon p. This is how we dealt with it in general chemistry, hopefully. That the p orbitals overlap to form a pi bond in a parallel relationship. A pi bond is what I like to call icing on the cake. It's not as strong as a sigma. It just adds a little bit of strength for us. So the pi bond is that side-by-side or parallel overlap of the p orbitals. The electron density of the pi bond is spread out above and below, right? It's all of this and all of this. It's like as if it's orbiting around that sigma bond, kind of like a donut. Pi bonds are weaker than sigma bonds, but they do exist in the same general idea. When we think about MO theory, molecular orbital theory, and we said bonding and antibonding, the same thing goes for a sigma or a pi. We like bonding MOs, right? So when we look at this little MO diagram, it's the same as what we had before. Just so you know that the pi interacts the same way as the sigma, just a different kind of overlap. So now ethyne, let's just amp it up one more time, or acetylene is what we call it. Each carbon in ethyne must bond to 2 other atoms, so only 2 hybrid orbitals are needed. If we again think about carbon's energy diagram for its valence, when we see that there's only 2 electron groups here for that carbon on the left, we only need to take 2 atomic orbitals, hybridize them to make 2 sp hybrid orbitals, and we'll have the leftover 2p orbitals as well. This would tell me 2 sigma bonds and 2 pi bonds. So we'll start to see some idea with hybridization and all of those lovely things. Counting up that 2 atoms can only have 1 sigma bond. Anything else, double or triple, all those extra bonds would be pi bonds. There's always only 1 sigma. So that carbon and this carbon are sp hybridized. Excellent. So if we wanted to think about the 3 bonds, there's always going to be 1 bond that is sigma. The sigma bond here for the 2 carbons is an sp to an sp overlap. And there are 2 pi bonds where it's carbon p to carbon p. The carbon to hydrogen bond is a sigma carbon sp to a hydrogen s. And again, there's 2 of them. We'll have a lot more practice with these in class. So looking at this 3-dimensional shape, we do see the 2 different pi bonds. One's there on the front and the back side interacting, and one's on the top to the bottom interacting. And they're, again, icing on the cake to what's in the middle, the sigma bond that's actually in the middle, direct overlap. That's how we get the linear shape. All right, so pi bond, because it's a parallel overlap, is weaker. The sigma bond is the direct overlap. It's stronger. Think about holding hands. I like to think about the pi bond as kind of like a high school relationship. You don't really hold hands, you just see each other, you're like, yeah, we're dating, but it's high school, so it's weird and awkward. Once you get in college, you can actually hold hands now, right? You're not afraid to hold hands anymore. Let's just keep it PC. I have a 3-year-old, remember? So the sigma bond is that direct overlap, holding hands. You are stronger, you are well established. It will always be stronger than the pi bond, which is the parallel or side-by-side overlap, not directly touching each other. Now, when we think about which one should be longer, the sp3 sigma bond or the sp sigma bond, the more s character, the shorter the actual orbital is itself. And so the sp3 is a longer bond, sp3 to sp3, because that orbital is actually longer, less s character, less like a sphere. The sp to sp sigma bond, that sp orbital is actually smaller. It's more s character, so it looks more like a sphere, and so it will hold the other atom closer. It'll be a shorter bond. We can also see the bond length and bond strength. A triple bond is the shortest bond at 1.20 angstroms. And it is the highest bond energy. It takes the most to break. The reason for that is because there are 6 electrons holding those 2 atoms together. There's 1 sigma and there's 2 pi's. All together, that would be 3 bonds or 6 electrons. For the double bond, again, that's 4 electrons. We have 1 sigma and 1 pi holding those 2 carbons together. And just for the single bond, the longest bond, the weakest bond, the bond energy that's the smallest cost, easiest to break, releases the smallest amount of energy when formed. we just have one sigma bond and no pi's there. Now with molecular geometry, this was what we were hinting towards with VSEPR theory. We will shift ourselves to just look at steric numbers or electron domains. We can also call them electron groups, depending on where you took your general chemistry. That's what we're talking about. Things around the central atom is like what I like to call them. Now, VSEPR theory is when we talked about electrons repel each other. Electrons repel other electrons. So electron groups or electron domains repel other electron groups. So when we think about that central atom having multiple things attached to it, multiple bonds or lone pairs, those things need to be spaced out and given their own room. We can't shove them all into corner. Nobody shoves baby into the corner. When you think about those groups, you want to make sure that they are not repelling each other and adding to the repulsion energy, which is the bad type of energy. So here are 3 different molecules, all with 4 electron groups. Let's just remember that idea that a sigma bond is an electron group, a lone pair is an electron group. So all of these have a steric number of 4, whether they're sigma or lone pairs. They all add up to 4. They would all be sp3 hybridized then. If a steric number is 4, you take the S, the P, and the P. You homogenize them together and you make sp3. If your steric number is 3, so for instance, let's look at BH3, right? Or we can think about this Lewis structure that we just did earlier in the week, CH2O. You take the S, the P, and the P, and you homogenize them together to make sp2. Physically 3 groups around there. Now what happened to that extra P? It's the pi bond right there. Pi and a sigma. Together that is 1 group, right? Now if the steric number is 2, think about carbon dioxide. We only have 2 electron groups. We only need 2 atomic orbitals. sp hybridized for that central atom. So when we think about our geometries and our organization of all of these, hybridization is attached to the steric number. Also what's attached to that is the idea of bond angles, right? And tetrahedral electron geometries. Now a tetrahedral molecular geometry, such as methane, is when where all 4 electron groups are sigma bonds. If we think about nitrogen and ammonia, NH3, with the 1 lone pair, this is a tetrahedral, but notice how the bond angle is a little bit smaller. Once we institute a lone pair, we get a different type of molecular geometry. This was trigonal pyramidal. It's important to remember that because the bond angle was less than 109.5. Less than 109.5, 107, please remember one of those. It's important to note that the lone pair takes up more room than a bond, gives those lone pairs more space. Oxygen and water is even more of a depressed bond angle. This is what we called the bent molecular geometry. Important to note all of those. Less than 109.5 or 105 is also good to note. The other ones that we want to remember, BH3 or BF3, when we had 3 bonding pairs, that was the trigonal planar. And if we have 2 electron groups, such as CO2, or this example from your table 1.3, BEH2, linear, right? Trigonal planar has a 120-degree bond angle. Linear has a 180-degree bond angle. We'll get to those right now. Steric number of 3, trigonal planar, sp2 hybridized. All of these go together. So when we are looking at the steric number, we get a lot of information from it. So be well aware of counting the things around that central atom. And we realize that boron has no formal charge here. Remember, he's the incomplete octet. He is sp2 hybridized because of those 3 groups around him. He still has an unhybridized p orbital, but it is empty on boron. Very important to remember. That p orbital is still there. Could be filled and be a pi bond, but for Bf3, it's unfilled and it's empty. When the steric number is 2, we remember linear. BeH2 is a good example. Carbon dioxide is one that we did too, so I'll redraw him here. Right. The p orbitals on carbon are being used. How can we tell? There's pi bonds. BeH2 has no pi bonds, so Be has empty p orbitals. Carbon is filled, we see the pi bonds. We'll be able to make those distinctions once we start getting more examples. So this chart is a great one to remember. We do need to know our molecular geometries. We'll practice them a lot, but notice how we only go to a steric number of 4. We don't care about 5 and 6 as we did in general chemistry. We're going to stick with these ones. Now, we talked about polar bonds. Let's talk about what that means in a molecule. Electronegativity differences result in polar bonds. Now, induction is the ability of shifting electrons within an orbital, and within a molecule, we can create something called a dipole moment. We will not be actually measuring any dipole moments or being able to report any dipole moments. All we really want to get out of this chapter is the idea of, is there a dipole moment, yes or no? Do I have a polar bond, and is the molecule asymmetric? So when we look at molecules with multiple polar bonds, what we really want to be able to say is, can we take the vector sum? Woo. So looking at this first molecule right here, chlorine to carbon is a polar bond, where the chlorines are delta minus and the carbon is delta plus. What does that mean of the overall molecule? Well, it's a vector sum. That overall, the polarity of the negative charge is in between the carbon or the chlorines, and the carbon still has that delta plus. Same thing with NH3. We have individual polar bonds resulting in a bunch of delta pluses on our hydrogens and a delta negative on the nitrogen. So overall, the polarity of this molecule points upward towards the nitrogen. Water has polar bonds. The overall polarity, the vector sum for that molecule points towards the oxygen, right? There is a net dipole moment in all of these molecules. Now, you have to know the molecule's geometry before analyzing the polarity, right? If you have not drawn the molecule with its proper geometry, you might actually assess it wrong. You might take the vector sum and forget what the actual molecule looks like. So for instance, if you just did water looking like this and you said it was linear, you might say that the vector sum would be net 0 because you forgot there's lone pairs and you forgot that that is bent, not linear. So be very, very careful when analyzing all of these. You have to understand and really value the overall idea of the geometry first before analyzing the polarity. We will be looking at electrostatic potential maps in class in a lot of examples. They look very colorful and very beautiful. The delta negative is usually the reddish color. The delta positive is more blue, purple. And what this just is our way of being able to visualize the electron density shift. Electrons reside with atoms that are more electronegative. And there is a deficiency with those electropositive atoms, things like carbons and hydrogens. Just a couple of polarity and dipoles that we can see. Here, these all have dipole moments. Ones to make sure you realize is that even though in the Lewis structure we would draw things like oxygens to carbons as linear here, remember this is bent. Geometry is important, right? Things like pentane, carbons to hydrogens, nonpolar, no net dipole moment. CCl4, yes, carbon to chlorine is a polar bond, but what is happening here is the overall vector sum is 0 because every chlorine is pulling the exact same way. I want to just present another one. Carbon to oxygen is usually polar, but in carbon dioxide, we have an overall 0 dipole. Dipole moment is 0 because of the equal symmetry within that molecule. Intermolecular forces we should have seen in the second semester of general chemistry, sometimes in the first, depending on where you look, but typically in the second semester. So this might be newer thoughts, maybe fresh in your mind. Solubility, boiling point, density, state of matter, things like that, they're all affected by the attractions of separate molecules. Now, thinking about intermolecular forces between two molecules, at least two. You can't just draw one molecule and try to find the intermolecular force. It's not going to happen. So thinking about the three, I've ranked them here from least pull to most pull. Dispersion forces, everything has London dispersion forces. They're fleeting, they're temporary dipole moments. Dipole-dipole interactions, permanent dipoles, these are relatively strong. And we'll see when they exist in a polar molecule interacting with another polar molecule. Hydrogen bonding, the strongest intermolecular force for a pure substance. Hydrogen bonding is a special or a super dipole. Now, if two molecules are nonpolar, they still do have attractive forces. This is where we get London dispersion forces. Everything has London dispersion forces. Nonpolar molecules normally have their electrons spread out evenly around the nuclei, balancing the charges, so we don't usually have delta pluses and delta minuses. However, the electrons are in constant random motion within their molecular orbitals. So we can induce a dipole. Look at these electrostatic potential maps. Delta minus can be induced when it gets close to something that is delta plus or has electrons. What will happen is we will induce a dipole. It is temporary, it is fleeting, it is not permanent in any way, shape, or form. These two molecules come together and say, oh, hey, I'm attracted. Okay, I'm gone. And it's done. They're very weak. And so every molecule will have these type of induced dipole moments. And these are called London dispersion forces when those two things attract. Opposites attract. So there is a little bit of attraction here, but it's nothing to write home about. When we think about these fleeting interactions, they are generally weak. If there's enough of them, they can add up to be significant. And we'll talk about that in a little bit. So the greater the surface area of the molecule, the more temporary dipoles are possible. So looking at some real life example, the feet of a gecko. They have many flexible hairs on their feet that maximize the surface contact. And so geckos can walk up the wall. They're using London dispersion forces to walk up the wall. They're interacting with the surface of the wall, whether it's a window or concrete or wood. They're interacting and sticking slightly because of the increased amount of surface area, a lot of flexible hairs that maximize that surface contact. And so they can add up. Really, really cool type of example there. So when we look at something in chemistry, we don't really map out the gecko's foot, but what we can see is as we increase the number of carbons, we actually are increasing the number of London dispersion forces. So if we see 4 carbons to 5 carbons to 6 carbons, hexane, 6 carbons, has more London dispersion forces, and it's holding those molecules in the liquid longer. Pentane has a little bit less London dispersion, less surface area, so it's a lower boiling point. Butane, smaller molecule, less surface area, less London dispersion forces, lower boiling point. Remember, London dispersion forces and all intermolecular forces occur in the liquid phase. Therefore, the molecule that has the most intermolecular forces wants to stay in the liquid phase longer. So higher intermolecular forces result in higher boiling points. Now, more branching in a molecule lowers its surface area. Think about the difference between we can think about a rectangle versus a circle. The actual rectangle is more surface than the circle. Circles are the least amount of surface area for the sphere. So the more branching, the more spherical. Notice that this central carbon is not really seen on the outside anymore. And so it truly is less surface area there. And so longer surface area, more intermolecular forces. And I'm just going to abbreviate that IMFs. These are London dispersion forces, simply because we're only dealing with hydrocarbons right now. But notice how our boiling point decreases to the less surface area. Less intermolecular forces, not as many things holding those molecules together in the liquid phase. Now, dipole-dipole attractions are permanent dipoles. It is a result when a polar molecule lines up with another polar molecule with the opposite charge, the delta minus to the delta plus, delta minus to the delta plus. There is the intermolecular force. That attraction between one molecule's delta minus and the other molecule's delta plus that is permanent in the molecule is a dipole-dipole interaction. These are stronger than the London dispersion forces, and so they have to be taken a little bit more seriously. When we think about a molecule like isobutylene that is not polar, it has a boiling point of negative 6.9. Acetone institutes that polar bond of carbon to oxygen. We see an actual delta minus and a delta plus. Permanent dipole, so therefore dipole-dipole interactions happen within a solution of acetone. Boiling point drastically increases. Notice the two similar surface areas and structures. So comparing apples to apples, not apples to kiwis. We'll get to the weird stuff in class. Hydrogen bonding are exceptionally strong. These are still intermolecular forces. They are not a type of bond like a covalent or an ionic bond. They are not as strong as a covalent or an ionic bond, but they are very strong attractive forces between molecules. So thinking about things that have a hydrogen bonded to an electronegative atom, small electronegative atom, oxygen, nitrogen, and fluorine, and its attraction to a lone pair on another electronegative atom, oxygen, nitrogen, or fluorine. So here is that polar bond, delta plus of hydrogen, delta minus of oxygen. The hydrogen bond exists right here. There's the H bond. When the hydrogen of one is attracted to the oxygen of the other. Notice this right here is not a hydrogen bond. That is a covalent bond. That is one piece of the puzzle to the intermolecular force, hydrogen bonding, but it is not the only piece. It signifies that there is a super dipole, but it needs a lone pair of an oxygen, nitrogen, or fluorine to go with it. All right, another one, delta minus on nitrogen, delta plus on hydrogen. Attracted to the lone pair of another. There is the H bond. Excellent. Wonderful. Now, only when a hydrogen shares electrons with a highly electronegative atom will it carry a large partial positive charge. And that large partial positive charge can attract the large delta negative charge on another molecule. So again, there it is. This one's the delta minus over here. There's the hydrogen bond. Even with these large partial charges, hydrogen bonds are still about 20 times weaker than a covalent bond. That should be a huge indication that they're not a true type of bond, just an intermolecular force. Excellent. Now, hydrogen bonding solvents can start to engage in hydrogen bonding if they are polar protic solvents. They have a polar proton. Hydrogen is a common term for a proton because if we think about hydrogen's nucleus, it has one proton, no neutrons. So therefore, a common term for hydrogen is a proton. A polar protic solvent we will use once we get into chapter 7. We'll use it a lot, and that will be really awesome. Now, if we again think about increasing the amount or the extent of the hydrogen bonding, we can start to see different boiling points. So trimethylamine, this guy right here, does not have hydrogen bonding. He has London dispersion forces, and he has dipole-dipole interactions. Ethylmethylamine has one hydrogen there attached to the nitrogen, so he does have all three types all the way up to H bonding. Very, very strong intermolecular forces there. So notice how his boiling point has increased from 3.5 for trimethylamine to 37 for ethylmethylamine. Now propylamine, 2 hydrogens. Lots of hydrogen bonding capabilities there. Yes, we still have London dispersion forces and dipole-dipole interactions, but notice how propylamine has the highest boiling point, strongest intermolecular forces out of these 3 because it has 2 areas to hydrogen bond versus just 1. Now, hydrogen bonds are common in things like DNA because they are what form the double helix, and some proteins to fold in an alpha helix. So thinking about hydrogen bonds, they are very prevalent in biochemistry and biology. For us, we're going to be looking at them in terms of solvent to solute interactions, similar to what you saw in general chemistry. And solubility. Like dissolving like. Hopefully we learned that in general chemistry, that polar compounds mix well with other polar compounds. If you have hydrogen bonding, you like to mix with other things that can hydrogen bond. Non-polar compounds don't tend to mix well with polar compounds. They tend to mix well with other non-polar things. So like dissolving like intermolecular forces, dissolve like intermolecular forces. And so we know it would be difficult to get a polar compound like water to mix with a non-polar compound like oil. So we can't just wash our clothes in just plain old water. We need soap, which has both polar groups and non-polar groups. So we can start to see how molecules that are big and huge might have polar portions and non-polar portions. So that's how we can start to look at molecules within this class, and within the context we can start to identify a polar portion or a non-polar portion. And the overall molecule, yes, we can establish if it's polar or non-polar, but it's really important to start breaking apart that molecule into its groups. That's something that we're going to start doing a lot of in this class. When given a molecule, break it apart, see what pieces it has, identify, yeah, there's a formal charge there. Yes, this is polar over here. There's delta minuses and delta pluses. This is non-polar, right? So start annotating things a lot more. Be comfortable with whittling down things that you might be able to see to help you think about reactivity. And we know soap forms micelles in water, which help carry away the dirt and be able to, get things clean with water. Thank you so much for joining me.